I am here again, and I'm about to start a series of videos on, as you were seeing from the heading there, integration and applications. Now, before I even get started, let me say that this series of videos, it's 3 of them. These videos are for my Add Math class, and they're also for the Pure Math Unit 1 class. The videos are compulsory viewing, and the problems that I'm going to assign are also compulsory viewing. In my Pure Math Unit 1 class, I know I'm working with students that are operating at different levels. Some who didn't do Add Math, some who did Add Math, some who did Add Math, but they're still not so good at it. Whatever the case is, these 3 videos, the first 3 introductory videos to integration and applications, are compulsory for both groups, the Add Math group and the Pure Math Unit 1 group. Later on, there's going to be a series of 3 other videos that will exclusively be for the Pure Math Unit 1 students, which will build on top of these. But I know for sure, for several of you, you need these 3. So even though they are for the Add Math group, they're also for you. Compulsory viewing and compulsory, the requirements for solving the homework problems, that's also compulsory. So please note what I just said. Without further ado, let's jump right in. Integration and applications. The first video, Introduction to Integration and Applications 1. I'm not sure why this is labeled 3 and this is 2. This should be 1 and this should be 2. Okay. So we're going to start with some basic definitions of what integration is all about. Number 1, integration is the reverse process of differentiation. In the same way as when we started differentiation, we said differentiation was the reverse process of integration, right? Remember that? So if I start with a function g of x and I perform this process of differentiation, I'll get some other function f of x. If I were to take this function f of x, as these arrows are clearly showing, I perform this process of integration, then I get back the function g of x. I usually get back that function plus something called an arbitrary constant, which we'll talk about a little later on. So that's the first way to think of integration, as the reverse process of differentiation, since differentiation itself was the reverse process of integration. The second way to think of integration, you think of it as an addition process. It's a special way to add. And in fact, in many cases, you think of integration as, if you're thinking of it as an addition process, you think of it as the limit of a sum. Limit of a sum. It'll make more sense to the people who are doing the Pure Math Unit 1, because y'all did a bunch of work on limits. And I'll talk more about this limit of the sum idea in the videos that will be exclusively for you, the Pure Math Unit 1 group, that is. All right, so those are the 2 ways to think of integration. Let's talk about what's called indefinite integrals. Indefinite integrals. An indefinite integral is defined as an integral without limits or boundary values. Okay. It'll become clear what the limits and boundary values are when we compare the indefinite integral with the definite integral. So, here is the way you indicate that you're integrating a function. Let me identify each term in this. This guy right here, this fancy looking elongated S, that's the integration sign. And it's used to tell me I have to integrate whatever is inside there. This is the function to be integrated, and that function is generally referred to as the integrand. f of x right there. That is the integrand. The result that you end up with is called the integral. That's what you were seeking, to find the integral of the function f of x. So this entire thing here, that's called the integral. The result of integrating the integrand gives you the integral. And the c alone, that's called an arbitrary constant of integration. You need to be familiar with all of those terminologies. By the way, I noticed I didn't identify this dx guy. Dx. The dx, that is usually like a tag along that kind of tells you the variable of interest. So if I'm integrating a function of x, then I have to tag along dx. If I'm integrating a function of y, I'll have to tag along dy. And in fact, it gives me some other information as well. It actually tells me when I have a definite integral, which we'll talk about later on, the ones, remember, that would have boundaries or limits. It actually tells me the variable associated with those limits. I'll talk about that again when we do definite integrals. So this dx is simply indicating the variable of interest. The function is a function of x, therefore that dx must tag along with it. If I had the integral of f of t, then guess what I would have to have there as the tag along? dt, right? All right, and so on and so forth. Okay, so the integration sign, and please, if you've never done integration before, practice a little bit to make it, right? It's not that bad. There are several cases for me. It's like an elongated S. All right, so the integration sign tells me to perform the process of integration. I have to perform this process of integration on a function, f of x, and that's called my integrand. The tag along dx tells me the variable of interest. If I'm integrating a function of x, then I must tag along dx there. The entire result that I end up with, which is some other function g of x plus c, the entire function is called the integral. So when you integrate the integrand, you get a result called the integral. And that c in there is an arbitrary constant of integration. You should always put it in there once you have an indefinite integral. Right? C, the arbitrary constant of integration C is only required when we have an indefinite integral. There. Okay, so that's just getting you familiar with the notation. All right? All right, integration. Let me move this line from here. All right, integration is the process that gives a result, which is integration is the process that gives a result, which is the indefinite integral, and that's also called that's another name that you use for it, by the way, an antiderivative. Very seldom used though. integral, or the indefinite integral is called an antiderivative. There. All right. Format's a little better there. Good. Now, you would remember, I always like to draw these analogies so that it kind of everything ties together. You would remember that when we started differentiation, the rule or the process that was required to differentiate a function was determined by what type of function you had. If we started out with a polynomial function, which we did, there was a special rule for that. And then later on, we switched to trig functions. Even in between there, we looked at more complex functions that require the use of chain rule and product rule and quotient rule and whatever else. You remember all that stuff, right? In the same vein, the process that's required, or the rule or rules that are required for us to integrate a function, will be determined by what type of function we have. And again, we're going to start with the most basic of functions, which is the polynomial function. So that's our heading right there. Right there. Integration of the polynomial function. The polynomial function looks like y is equal to ax to the n. Notice the rule I'm about to give you will work in every case except when n is minus 1. N cannot be minus 1 for us to apply this rule. If n is minus 1, the rule I'm about to give you will not work. So please make sure you remember that restriction. This is the integral of ax to the n where n is not minus 1. Okay, here it is. The integral of ax to the n dx gives me a function that looks like ax to the n plus 1 divided by n plus 1 plus c. And let me repeat it here. Note, n must not be minus 1. If n is minus 1, the rule will not work. All right. Let's get into our first integral. The integral of a, which is a constant, dx. If I have a dx, dx tells me the variable of interest. But if I have the function which is just a, then clearly a is a constant with respect to x. Now, how do I integrate that? Well, the hard and fast mathematical way to do this is to rewrite it as the integral of a times x to the 0 dx. Think about that. X to the 0 is 1, isn't it? And 1 times a will give you back a. So by writing it as a times x to the 0, I've written it in terms of ax to the n. I remember the only restriction is that n must not be minus 1. They didn't say anything about n not being 0. So that power n could definitely be 0, as I've shown there. And therefore, the integral of ax to the 0 dx would be a times x to the 0 plus 1, n plus 1 upon n plus 1 plus c. The result in this case, x to the 0 plus 1 is just x to the 1, or x, divided by 1 is just x again. So the result is ax plus c. Think about it logically. By now you should be good at differentiating. If you differentiate this result, the ax plus c, you differentiate the ax, you get a. Differentiate the constant, you get 0. So you get back the a. Okay, simple enough. Let's try another one. The integral of 5x squared. Well, that's in the form of a polynomial as well. Integrating 5x squared will give me 5x to the 2 plus 1 upon 2 plus 1 plus c, which is 5x cubed. 5x cubed upon 3 plus c. And I'm going to stop doing the 2 plus 1 and the 3 plus 1. You can do that in your head. All right, so far so good. Let's tackle the next one. The integral of 2x cubed minus 5x squared plus 7x minus 4. Well, each part looks like a polynomial. And does integration distribute over addition and subtraction? The answer is yes, which means we could integrate each part separately and then add the results together. So let's see how this one is going to work. And I have a note next to it that says effectively the distributive law works. The distributive law of integration over addition and subtraction. So let's apply the rule for ax today. And this would be 2 times x to the 3. Well, I'll do what I said. 3 plus 1 is 4. Over 3 plus 1, which is 4. Minus 5 times x to the 2 plus 1, which is 3, upon 3. Plus 7 times x to the 1 plus 1, 2, upon 2. Minus 4. When we integrate the 4, we get 4 times x. Integrate a constant, as we saw up here, we get the constant times x. So minus 4 times x plus c. If I were to simplify that a bit and write it as a standard polynomial, because whenever you're writing a polynomial, you should write coefficient and then the term with x. So the result here is 2 upon 4, that's a half, times x to the 4th, minus 5/3 times x cubed, plus 7 halves times x squared, minus 4x plus c. That's not too bad. How about the next one? Give me a minute, let me tidy things up here. Yeah, let's try the next one. The integral of 5x plus 2 times 3x squared minus 2. Does integration distribute over multiplication? Because you have one bracket multiplied by another bracket. And the answer to that is no. Integration function or operation, I should say, only distributes over addition and subtraction, not multiplication or division. So what we have to do is to take that function and massage it in such a way that each part looks like a polynomial. So let's see, this becomes the integral of, this will become the integral of 5x by 3x squared. That's 15x cubed, looks like. Double check my arithmetic there. 5, 3 is 15x cubed. 5x by minus 2 is minus 10x. 2 by 3x squared. 2 by 3x squared is 6x squared. And 2 by minus 2 is minus 4. All times dx. Let me write it in the standard form in descending powers. Integral of 15x cubed plus 6x squared minus 10x minus 4. All times dx. And we'll apply the standard rule to each part. When we integrate, this becomes 15x to the 4 upon 4 plus 6x to the 3 upon 3 minus 10x to the 2 upon 2 minus 4x plus c. If we tidy that up, 15/4 x to the 4 plus 6 upon 3, that's 2, x cubed. 10 upon 2, that's 5, so minus 5, x squared minus 4x plus c. That looks pretty good as well. Let's try the next one. How about 2 minus 3x all squared? Well, as of now, because we only know one rule, we're going to apply that one rule to try to integrate this function. And to integrate it, the entire thing must look like a single polynomial. So I would have to expand those brackets first. And the obvious question would be, suppose it wasn't a square, like a 5th power or a 6th power. Would I still have to expand the brackets? Well, only if you want to, but clearly that would not be efficient. So, well, in this case, let's just worry about our power, which is 2, and we could expand that with no issues. This one becomes the integral of square root of first minus 2 times first times the second. 2 2 is 4 by minus 3 is minus 12x and plus 9x squared. And I'll leave it in this order. No harm with that. Dx. Give myself a little space here. Okay. Integrate the 4. I'll get 4x minus 12x to the power 1 plus 1 is 2 over 2 plus 9x to the 3 over 3 plus c. If I tidy this up, and I can write it in descending powers now, the result will be 9 upon 3, that's 3x cubed, plus, minus 12 upon 2 is, that's minus 12 upon 2 is minus 6x squared, plus 4x, and then put the c at the end. There. So, no big deal there as well. Seems pretty straightforward. All I'm doing is applying the rule for integrating a function that looks like a times x to the power n. Integrating a function that looks like a times x to the n. Okay, how about the next one? Root x minus x root x. Well, I gotta massage this as well. Everybody knows their indices. Root x can be written as x to the power of a half, and that would be in the form ax to the n, right? 1 times x to the half. So I can use a little bit of indices and massage that function first. So I still have to put back the integration sign. Integral of x to the half minus x times x to the half, all times dx. But integration does not distribute over that multiplication there, so I have to merge those two into one. So I'm still massaging the function. Most times what I would do, if I have to massage a function first, I'll pull it out, work on it, and decide, and then put it back in the integral. I'll show you in the next example. So I still have to put back the integration sign here. Integral of x to the half minus, and x times x to the half is x to the 3 halves, right? Now each part looks like ax to the n. I can integrate. This becomes x to the half plus 1, that's 3 halves, divided by 3 halves, minus x to the 3 halves plus 1 is 5 halves, divided by 5 halves, plus c. If I tidy this up, if I divide by a fraction, everybody knows by now you upturn and multiply. So this would be 2/3 times x to the 3 halves minus 2/5 times x to the 5 halves, like so. Now if you want to write this back with the roots, you can write it as 2 times the root of x cubed upon 3 minus 2 times the root of x to the 5. That would be x to the 3. X to the 5, yes, I'm right. Upon 5 plus c. I forgot my plus c there. And that's the integral for that guy right there. Okay. Let's deal with this next one. It's now the integral of a quotient expression. Alright, so instead of dragging along the integration sign, what I will do is something like this. This is one of the favorite things I usually do. I say consider, and in this case I'll just consider the integrand, which is the 4 minus 3x all squared upon 2 root x. And what I'll do, I'll massage it until the entire thing looks like a single polynomial, put it back into the integral, and perform the process of integration. Okay, open up the numerator. That's 16 minus 2 4 0 3 is 24 That looks like 24x, yes. 24x. 2, 3, 6, 4 is 24. And plus 9x squared. Yes, plus 9x squared. All divided by 2 times x to the half. And then now what I'll do, I'll break this up into 3 separate fractions. This would be 16 upon 2x to the half minus 24x upon 2x to the half plus 9x squared upon 2x to the half. Okay, let's simplify each fraction. 16 over 2, that would be 8. Remember, I have x to the half in the denominator, so if I throw it up, it will become 8x to the minus a half. That makes sense, people? 8x to the minus a half. Right? 16 over 2 is 8. The x to the half, which is still in the denominator, goes up. Becomes x to the minus a half. 24 upon 2, that's 12. And x on top divided by x to the half. Remember, when you're dividing with the same base, you subtract the powers. X to the 1 minus x to the half is just x to the half. I should say x to the half. Let me say that again. X divided by x to the half is the same as x to the power 1 minus a half, which is x to the half. There. Plus 9 over 2, I can't break that down, so I'll leave it as is. 9 over 2, and then x squared divided by x to the half is x to the power 2 minus a half, which is x to the power 3 halves. So, what have I done so far? I haven't integrated this yet. All I've done so far is to take this guy and massage it to look like this guy. Right, massage it. Ooh, what am I doing? Massage it to look like this guy here. So, if I go back now, I can say the integral of the original expression, which was 4 minus 3x all squared, all upon 2 root x dx, can now be written as the integral of the new expression, 8x to the minus a half minus 12x to the half plus 9 halves times x to the 3 halves, all times dx. And now I integrate because each part looks like a polynomial. This is 8 times x to minus a half plus 1 is a half divided by a half minus 12 times x to the power half plus 1 is 3 halves over 3 halves plus 9 halves times x to the power 3 halves plus 1, which is 5 halves, upon 5 halves plus c. My job now is to massage this and make it look nice. Whenever you divide by a fraction, you upturn and multiply. So upturn the half, you get 2. 8 to 16 x to the half minus. Upturn the 3 halves, you get 12, 2 is 24 over 3 is 8. Double check my arithmetic there. 8x to the 3 halves, like that. Plus 9 halves. Now I gotta remember, I gotta upturn the 5 halves to get 2 fifths. So those two will go out and I end up in 9 fifths. There. So 9 fifths times x to the 5 halves plus c. And if I want to write it with a root, then simple. 16 root x minus 8 root of x cubed plus 9 root of x to the 5th upon 5 plus c. How you like them apples? Them apples nice. Those apples are really sweet. Right? So I've gone through a whole stack of integrals. You should review them. If this is the very first time you're going through them, it's a mixture of the regular polynomials, right? Regular polynomials. And then a function times a function. You got to open it up to make it one polynomial. Then you got a function to power. You got to open that up, make it one polynomial. And then you have your, you're going to throw in the radicals in there and the roots. You got to show that you know your laws of indices to merge the function into a single polynomial again. And then the ratio of two functions, which you got to massage and put it in the form of a single polynomial and integrate. So there's a wide variety of different problems there, but all at the end of the day, all of them use that one rule, which is the integral of ax to the n is a times x to the n plus 1 divided by n plus 1 plus c, where n must not be minus 1. Don't forget that part. Every time you say it to yourself, repeat that part, where n must not be minus 1. And the reason that's important is because when n is minus 1, you get a totally different rule and an integral. It actually ends up being a log function. But that's only for the pure math, unit 1 people and higher. So always repeat to yourself. The rule is the integral of ax to the n dx is ax to the n plus 1 over n plus 1, where n must not be minus 1. N must not be minus 1. N must not be minus 1. You understand what I'm saying it? Good. Y'all do the same thing. All right. That's the first category. Let's look at the next category of functions that you have to integrate. Integrating a function of the form y is a function of x to the n. Now, in this case, you have two restrictions. There are two restrictions here. So, be careful. All right, so I'll give you the rule for that. The integral of f of x to the n dx. By the way, the restrictions are f of x is linear. A linear function is written in the form ax plus b, like that. And the same old restriction, n must not be minus 1. The integral of f of x to the n dx, where f of x is linear and n is not minus 1, is this expression. 1 divided by f prime of x times f of x to the power n plus 1 divided by n plus 1 plus c. Mercy. I'll put this whole thing in a box because you need to learn it properly. All this. The whole thing. There. I'll read it again. Integral of f of x to the n dx is 1 divided by f prime of x times f of x to the n plus 1 upon n plus 1 plus your arbitrary constant c. But this rule is only applicable when f of x is linear. That means it's written in the form ax plus b. And n is not minus 1. So whenever you're integrating, you have to go through that checklist before you actually apply that rule. Don't just apply it blindly. Okay. Oh, one thing I forgot to stress in there is the f prime of x bit. Right there. 1 upon f prime of x. This guy right there. Remember what f prime of x is? F prime of x is the derivative of f of x. You're differentiating the f of x. So even this rule, which is a rule for integration, part of the process of integration requires that you differentiate. Isn't that nice? That is so nice. So let's see if we can apply it here. The first function, or the first integral, the integral of 5x minus 7 all squared dx. Let's go through the checklist. The function inside the brackets, the 5x minus 7, is that linear? Yes, it is, because it's written in the form ax plus b. The a in this case is 5, the b is minus 7. So it is in the form ax plus b, 5x minus 7, just the part inside the brackets. That's linear. How about the power n? Is that power not minus 1? That is a true statement. The power is not minus 1, and therefore I can apply the rule as shown above. You see how I went through the checklist first instead of just jumping in and starting integrating? All right. So here I will have, this is equal to 1 upon the derivative of the part in the brackets. Now 5x minus 7, you know how to differentiate that with your eyes closed, with your eyes open, anything. When you differentiate 5x minus 7, you just get 5. So 1 upon f prime of x is 1 upon 5 times the same f of x, which is 5x minus 7 to the power n plus 1. In this case, n is 2. So 2 plus 1, that's 3. Upon n plus 1, which is 3, plus c. All I got to do now is tidy that up. In my numerator, I have 5x minus 7 all to the power 3 divided by 15. I can either divide by 15 or put 1 upon 15 in front. I can put 1 upon 15 in front. Right? The 5 in the denominator by the 3 in the denominator gives me 15 in the denominator. So I can put 1/15 in front like that. And then plus c. Voila. Not too bad. By the way, just let's do a quick side check here. Side check. If you remember, if this function right here, if I were to differentiate it using, you remember what the rule, chain rule? So that would be, if I drop the power, that would be 3 times 1/15 times 5x minus 7 to what power? I got to subtract 1 from the power to give me back 2, right? Times, and then you differentiate inside the brackets to get what? 5. Okay, well, 3 into 15 is 5. Yes, 3 into 15 is 5. The 5 in the denominator will cancel out with that 5 on the outside. Or you can say, yeah, 3 over 15 is 1 over 5. 1 over 5 times 5 will give me 1. So this just becomes, oh, and of course when I differentiate the c, I get 0. So I just end up with 5x minus 7 all squared, which looks very much like my integrand. So it appears as if I did the integration correct. Now, always remember there are restrictions when you integrate. Remember when we were differentiating, we had no restrictions. We had 0 restrictions on n. But now that we're integrating, you got restrictions on n, you got restrictions on f of x, all kinds of fancy things. So keep that in mind. I'll keep stressing it right through the video. All right, let's move on to the next one. Partition this one off here. Yeah. Ooh. There. All right, the next one. The integral of 1 minus x all to the 5. Okay. Is it written in the form f of x to the n? Yes, the f of x is the part inside the brackets, the 1 minus x, and the power n is 5. Go through your checklist. Is the f of x linear? Yes, it's 1 minus x. Is the power n anything other than minus 1? Yes, it is. It's 5. All the conditions are met. Therefore, I will integrate as follows. It's 1 over the derivative of what's in the brackets. When I differentiate what's in the brackets, the 1 minus x, I will get minus 1 times the f of x, which is 1 minus x to the power of 5 plus 1, which is 6, over 5 plus 1, which is 6, plus c. Can't get any easier than this. So the 1 over the minus 1 is minus 1 in front. So I'll just put minus 1 upon 6 into 1 minus x to the power 6 plus c. Too simple. Too simple. Y'all agree? I know they didn't agree. Let me make some space here. All right, let's tackle the next one. How are we tackling this one? Integral of the square root of 6x minus 11. Well, that's no big deal. Everybody knows how to do that. Even I could do this. Watch, check this out. I'll simply remove that square root and put 6x minus 11 to the power of a half. So this becomes the integral. The integral of 6x minus 11 all to the power of a half dx. And now the function looks pretty much like f of x to the n, where f of x is linear and n is not minus 1. The rule is 1 upon f prime, 1 upon the derivative of inside the brackets, 1 upon 6, times the f of x, 6x minus 11, to the power n plus 1, which is a half plus 1, that's 3 halves, divided by 3 halves, plus c. That's equal to, create a little more space here. Yes, that's equal to 1/6. I will upturn that fraction and multiply. Upturning 3 halves, you get 2/3 times 6x minus 11 to the 3 halves plus c. 2 upon 18 is 1 upon 9, or 2 into 2, 1, 3, 1/9, yes. So this entire thing becomes 1/9 into 6x minus 11 to the 3 halves plus c. And if you want to write it with a root, you can write it as the square root of 6x minus 11 all cubed. And I'll put the 9 on the bottom. 1/9 multiplied by 1/9 is like divided by 9 plus c. Yeah, you can write it like that as well. No harm. Okay, we're making good progress, I think. In my mind, we are. Are we? Y'all understanding these? No. All right, let's do the next one. Well, the rule didn't cater for 1 upon anything. The rule did not cater for 1 divided by. How are we going to handle this one? Well, at least we can start out by rewriting it as the integral of 1 upon 6x minus 11 to the power of a half. But the rule is not for 1 upon f of x to the n. The rule is for f of x to the n, isn't it? So all I'll do is throw the entire denominator up into the numerator. So this becomes the integral. I'm not integrating as yet, so I got to write back the integration sign. Integral of 6x minus 11 all to what power again, people? Minus a half. All you do when you transpose an entire expression from the numerator to the denominator, or vice versa, you change the sign and the power, times dx. So 1 upon the integral of 1 upon the root of 6x minus 11 dx becomes the integral of 6x minus 11 to the minus a half dx. Again, go through your checklist. F of x is linear. 6x minus 11 is linear. N is not minus 1. I'm allowed to apply that rule. It will be 1 upon f prime, which is 1 upon 6, times the function 6x minus 11 to the power minus a half plus 1, which is a half, divided by a half, plus c. Okay, upturn the half and multiply. So this becomes 1/6 times 2 over 1 times 6x minus 11 to the power of a half plus c, which finally gives me 2 over 6 is a third. And I can write the 6x minus 11 to the half as the root of 6x minus 11 plus c. Voila. You're doing pretty good. At least I hope we are. Okay, so how about this one? Integral of 5 divided by 6x minus 11 all squared. Well, it looks like we're not going to deal with a quotient here, so we're going to just throw the entire denominator up into the numerator. And this becomes the integral of 5 times 6x minus 11 to the power minus 2 dx. Now the 5 in front, the constant times the function shouldn't affect anything. In fact, you're allowed to pull a constant outside of an integral. So I'll show you in this case. You don't have to in this case, but I will. 5 comes out times the integral of 6x minus 11 to the power minus 2. So this would be 5 times whatever I get when I integrate that function in there. And it's in the form f of x to the n. So that will be 1 upon f. It's in the form f of x to the n, where f of x is linear and n is not minus 1. So that will be 1 upon the derivative of the 6x minus 11, which is 1 upon 6, times 6x minus 11 to the power minus 2 plus 1, which is minus 1, upon minus 1, plus c. Okay, let's tidy that piece up in front. I have 5 in my numerator. I have 6 in my denominator. I'll pull the 6x minus 11 to the minus 1. I'll put it back down into the denominator to make that power positive. And the 5 times the 1, 6 times the minus 1 would give me minus 5. Minus 5 upon 6 times 6x minus 11 to the power positive 1 plus c. Understand that? The 5 stays on top. The 6 is already in the bottom in my denominator. The 6x minus 11 to the minus 1 comes down to join it to become 6x minus 11 to the plus 1. And the minus, you could float the minus to the top. It could have either gone on top or the bottom. I could have written that minus here if I had chosen to. But I like it on top. So you could either float to the top or the bottom. There. And that's a pretty good workout on those types of functions. Integrating f of x to the n. Let me repeat. Where is the rule that I have on top? There it is. Integral of f of x to the n dx, where f of x is linear and n is not minus 1, gives me 1 upon f prime of x times f of x to the n plus 1 upon n plus 1 plus c. Okay, so that takes care of that part, or that type of integral. All right, now integration of trig functions. Well, for this section, for this portion of integration, you don't have much to do with trig functions. So I'll go through them. You can use each one as if it were like a little rule. All right, the integral of sine x gives me minus cos x plus c. You would remember when you differentiated sine, you got positive cos. So when you integrate sine, you get negative cos. Don't forget, and you must have a plus c if it's an indefinite integral. The integral of cos x is positive sine x plus c. Again, you'd remember when you differentiated cos, you got minus sine. So when you integrate cos, you get positive sine. Okay. How do you integrate how do you find the integral of sine of a function of x dx? Where f of x is linear again. This linear business where f of x is linear. So the rule is as follows. It's 1 upon f prime of x times, sorry, it's minus 1 upon f prime of x times the cos of f of x plus c. I'll do an example right now. Well, I got examples below. I got several examples below. All right. And then the integral of cos of f of x dx, that where f of x is linear again, that will be 1 upon f prime of x times the sine of f of x plus c. Let me move this out a little further. There. So those are your rules. Integral of sine x gives minus cos x plus c. Integral of cos x gives sine x plus c. Integral of the sine of f of x dx gives me minus 1 upon f prime of x times the cos of f of x plus c. F of x must be linear. Integral of cos of f of x dx is 1 upon f prime of x times the sine of f of x plus c. Again, f of x must be linear. Okay, so let's try some of these. First example, 5 times the sine of 2x. Well, 2x is in the form f of x, and it's linear, right? 2x is a linear expression. Remember how I was factoring out pulling the constant out of the integral? I don't have to. So in this case, I'm not going to do it. So I'll just write back the 5 times, and then I'll integrate the sine 2x dx. Well, the integral of sine of f of x is, as you remember, minus 1 upon the derivative of the linear function. In this case, the linear function is 2x. So when I differentiate 2x, I just get 2. So minus 1 upon f prime is minus 1 upon 2 times the cos of 2x, cos of the same f of x, plus c. Tidy that up a little bit in front, get minus 5 halves times cos of 2x plus c. What about the next one? 2 times the cos of 3x minus pi upon 6. So let's integrate. I'll write back the 2 first. And now I have to integrate cos of 3x minus pi upon 6. Well, again, that is in the form cos of f of x, where f of x is linear. So what would I get? Positive 1 upon f prime this time. 1 upon f prime would be 3. Right? If I integrate 3x minus pi upon 6. By the way, pi upon 6 is a constant. Pi is a constant, 6 is a constant, pi upon 6 is a constant. If you differentiate that, you get 0. So when you differentiate the entire 3x minus pi upon 6, you just get 3. 1 upon f prime, 1 upon 3, times the sine of the same f of x, which would be 3x minus pi upon 6, plus c. Tidy up, and I get 2/3 times the sine of 3x minus pi upon 6 plus c. Differentiate that back, you'll see you get back exactly the 2 times the cos of 3x minus pi upon 6. Because you should know how to differentiate that. The entire final expression that I got there. Okay. Let's tackle the next one. 7 sine of 4x minus pi upon 3. Okay, 7. I'll write back the 7. It's 7 times, so 7 times. The sine of 4x minus plus the sine of 4x minus pi upon 3. That's in the form sine of f of x, where f of x is linear. So when I integrate that, I get negative 1 upon f prime. Negative 1 upon f prime. And 4x minus pi upon 3 is f of x, so f prime would just be the 4. Negative 1 upon 4 times, integrate the sine function, I get cos of the same 4x minus pi upon 3 plus c. There. Okay, tidy up a little bit. The fraction in front, I get minus 7/4 times the cos of 4x minus pi upon 3 plus c. Okay. And the last one I have in this is the difference in the integral of the difference of two trig functions. Well, that shouldn't be such an issue because integration, you remember, distributes over addition and subtraction. So I'll simply apply the appropriate rule to each part, integrate each part, and take the difference. So this gives me 2 times, the first part is in the form sine of f of x, where f of x is linear. So that would give me minus 1 upon f prime minus 1 upon 3 times the cos of 3x. And then write the minus 3, which is the constant in front of the cos 4x. Cos 4x is in the form cos of f of x, where f of x is linear. So that will be 1 upon f prime, a positive 1 upon f prime, 1 upon 4 times the sine of 4x plus my arbitrary constant c. If I tidy up all the fractions and whatnot, I end up with minus 2/3 times the cos of 3x minus 3/4 times the sine of 4x plus c. And that brings me to the end of my first video. There's a lot of information in here if you're only seeing this for the first time, which most likely will be the Add Math people and some people from my Pure Math Unit 1 group. If you have to go to the video over 2-3 times, no problem. Make sure you understand all the rules, how and when to apply them. Okay. All right, now the worksheet comes from the Add Maths text, the Raymond Tulsi text. Again, everyone is responsible for these problems. Everybody's responsible. I didn't give that many. 7B, 10B, 6B, 10B, 10B. There are only 5 problems there. I think they give you a workout and whatever I have up there. I should have given more. Never mind. I want to find y'all. I'm going to see y'all on Zoom pretty soon. So you're going to have to explain to me all this stuff that I've been posting online to you, to my satisfaction. Doesn't that sound nice? Of course, I know y'all like explaining things to me. Yes. Let's see. So y'all should have that. Well, all the Add Math people should have the text, and so for the Pure Math Unit 1 people who did Add Math last year and may have the text, can you please post these problems in the Pure Math Unit group for the people who might not have that text? Thanks. All right, well, I will say goodbye to this video and I'll immediately start the next one, Integration and Applications 2. This is going to be nice. All right, so that's it for this one. I'm out.